Hello and welcome back to Master Meteorology Advanced. In this episode, we're going to be talking about the continuity equation. Alright, welcome back to the series covering the governing equations of meteorology. In this episode, we're going to be talking about the continuity equation. So, when you watch this video, don't worry about taking notes. You can either click the link in the description or go to holthanleyweather.com to download this PowerPoint. Just, I would say, try to watch it and see if you can pick up and just kind of get a general idea of what the continuity equation means. One other thing, this first slide is a little boring and a little slow, but the next slide is a perfect little picture that will just completely help you understand this concept. So first, we're going to start with the continuity equation. Del dot V plus d omega dp equals 0. First thing you want to do, whenever you see that del symbol, this one right here, looks like an upside down triangle, you're going to want to expand that into its components, and the same with V. You want to do this basically not just in continuity equations, but pretty much any meteorology equation where these terms come up, which happens to be almost every single meteorology equation. So the del expands to d dx plus d dy. And then the V, which represents our wind component, expands into u plus v. You can think of u as the zonal wind. It is from San Francisco to New York, whereas v is the meridional component. That's like San Francisco to Canada. Those are on the same plane, which is the horizontal plane. So you're going to expand those and then do the dot product. So you have del dot v, or when we have our expanded terms, d dx plus d dy dot u plus v. And if you don't understand how a dot product works, you multiply the like terms together. So the two things that are dealing with the east-west direction, the zonal direction, or the I direction, that all means the same thing, you're going to put those together. So our d dx goes into our u, so we get du dx. The d dy goes into our v, so we get dv dy. Now we're going to rewrite the equation. So there's our original equation. We're going to take this expanded version and plug it in for that del dot v. So we now have du dx plus dv dy plus d omega dp equals 0. And then think about what these represent. Du dx, that's east-west. dv dy, that's north-south. So those are both on the same plane. D omega dp, that's dealing in the vertical. So we're going to want to put that to its own side. And you'll understand better in a second why when we define the terms. So now we have those two on the left and one on the right. What do they mean? Horizontal divergence equals vertical motion. So how u changes, that east-west wind, with respect to x, plus how v changes, north-south wind, with respect to y, equals vertical motion. Omega represents vertical velocity with respect to pressure. So you could think of it as vertical wind in a way. And that's going to make a lot more sense once you see this picture. So here we have horizontal divergence equals vertical motion. Now, here we have du dx plus dv dy greater than or equal to 0. Probably doesn't mean that much to you yet. So what we're going to do, just ignore that v and y term for now. Doesn't matter with regards to this picture. Just think of this as your positive x direction and this as your positive z direction. Really, the big thing is that is our positive x direction. So if you think about this arrow right here, this represents wind. And this one is going in the negative x direction. So let's put a number on it. We'll call it negative 5 meters per second. And then as you go forward in x direction along the x-axis, this one is now positive. That's going to be some positive u in the positive x direction. So we'll say that's 5 meters per second. So in general, we want to look at du dx. How is u changing with respect to x? Well, it's going from negative 5 to a positive 5. that means du dx is positive. And when that is greater than 0, you think of that as divergence. If the whole math part of that doesn't make sense, well, it makes sense just by looking at the picture. If you have wind going this way and this way, you're going to get divergence. But something happens here. If the wind separates, we can't just have a vacuum. The mass completely left the area, and there's an important equation of physics, conservation of mass. I almost said conversation of mass. Conservation of mass. So if mass leaves an area, well then something's got to replace it, because there can't just be a vacuum. So once that divergence happens, it's going to lead to vertical motion. Hence our equation, horizontal divergence equals vertical motion. And in this case, it's upward vertical motion, which is important in meteorology because that ends up happening, or ends up being responsible for storm development and basically everything exciting that happens in meteorology. But something else happened. Once that wind goes up, now we have a vacuum at the surface. The mass left, so now mass has to fill in. So then you get convergence at the surface. You can imagine the opposite can also be true. So now we're back aloft. Think of this as like 500 millibars. Now we got 5 meters per second on the left side. As we go forward in the x-axis, then we have negative 5 meters per second. So we have positive 5 to negative 5. I think you can see that du dx is now negative. We're going from a positive, a big number, to a smaller number. So du dx is negative. So it's less than 0, which means convergence. If the math aspect doesn't make sense, the picture probably will. That's going to converge. Whoever named these did a good job. It pretty much explains themselves. But now, instead of in the last one where we had the mass leave the area, now we have a buildup of mass. And now that's got to go somewhere. So it rams together like this, and then it pushes down. So that's going to lead to downward vertical motion. And then that downward air can't just go straight through the earth, so it's going to lead to divergence on the surface. So once again, divergence aloft leads to rising motion, which leads to convergence at the surface. Convergence aloft leads to downward vertical motion and divergence at the surface. Quick summary of the video. The continuity equation tells us that horizontal divergence of the wind field is directly related to vertical motion. Du dx plus dv dy equals negative d omega dp. The continuity equation is a mathematical relationship that expresses conservation of mass for a fluid. If mass leaves an area, then mass is going to have to fill in. If mass moves into an area, then it's got to go somewhere. Last but not least, divergence aloft will produce vertical uplift, which will produce convergence at the surface. Convergence aloft will produce downward motion, which will produce divergence at the surface. If this didn't make a lot of sense the first time, watch it again, go through the PowerPoint on your own, and hopefully it can start to make sense because this is a really important topic and kind of idea to understand that explains basically all the exciting weather that happens in meteorology. I hope you enjoyed the video. Thanks for watching. As a reward and thank you for watching the entire video, I'm giving you a free PDF download of the video slides so that you can go back over the material, and a free PowerPoint download so that you can go through it step by step. You can find those resources by clicking the link in the description or by going to holthanleyweather.com. As always, if you learned something new in this video, click subscribe so that you can learn more in the future, and click more videos to start that learning now. Thanks for watching.